Hello everybody. Hope everyone had a nice few days off. We're right back at it. So we're going to continue with acid-base notes, and we're going to deal with buffers today. So what the heck is a buffer? It's a solution. They're solutions that have the ability to resist pH change when an acid or base is added. Now, in biology, buffers are very important, right? So when you're talking about any type of living organisms with fluid in them, those fluids have to stay about the same pH, right? So for example, our blood, there's a lot of stuff in our blood, right? But the pH of blood has to stay about the same. It can't change. If we have big swings in pH, right, that would kill us instantly. So our blood is an example of a buffer. Right? It's a solution that doesn't change pH very easily. Right? Now, there are really two types of buffers. Okay, we can make buffers with a weak base and the salt of that base or we can use a weak acid and the salt of that weak acid. Either one will work. Now, in reality, buffers are really just another type of common ion. So buffers are really common ion problems. So now we have choices between weak bases and weak acids to the type of buffer solution that we want to make. So sometimes we'll want a buffer solution maybe neutral around 7. We might want acidic buffers or basic buffers depending on the situation. All right, so by choosing appropriate solutes and concentrations, a buffer solution can be created for any pH. Right, so now you need to be able to look at a buffer system and decide, is it going to be an acidic buffer or is it going to be a basic buffer? And it's easy to do. So let's try this. Let's identify these buffer systems as acidic or basic. I'll give you 3. NH3, NH3NO3, KNO2, and HNO2, and KCl, HCl. So let's look at each one of these systems and decide what type of buffer it is. So if we look at the first one, right, we have to decide what we got here. So NH3 is what? Well, this is a weak base. This is a weak base. This is the salt. Ooh, this should be sorry, this should be NH4. NH4NO3. This is the salt of that weak base. This would form a basic buffer. Okay, let's look at the next one. Well, KNO2 is a salt. Okay, what type of salt? Well, if we look over here, this is what? This is a weak acid. This is the salt of that weak acid. Okay, so in this case, it would be an acidic buffer. All right, let's look at the last one. Well, KCl is a salt. HCl is an acid. So you would think this would be an acidic buffer, but it's not. Why is this not an acidic buffer? This is a strong acid. Okay. Strong acids or strong bases will not form buffers. Okay. So this one is not a buffer system. All right. So let's talk about how it actually works. So let's say we have let's use, I guess let's use this system, okay, this KNO2 HNO2 system. So first thing we're going to do is we're going to take our salt and we're going to dissolve it. So we know that KNO2 is going to completely ionize by molecular attraction into K plus aqueous and NO2 minus aqueous. All right, so all of it's going to come over here. Okay, now let's look at our weak acid. If we take HNO2, it will form an equilibrium with H plus aqueous. This is aqueous. And NO2 minus aqueous. Well, notice we have a common ion. We have a common ion between these, right? Now, when we put these together, what do we actually have in solution? When we put these together, this is all dissolved and become this. So if we were to put this all together, we would have HNO2 aqueous in equilibrium with H plus aqueous plus 2NO2 aqueous plus K plus. Now, who remembers what this thing is? Okay, what's the name of K plus in this system? Hopefully you remember that this, or K plus, is a spectator ion. Okay, it's not really taking place in the reaction at all. Okay, so we have the spectator ion going on. So we have this in solution. This is actually our buffer. Right? It's going to resist pH change. Why? Well, because of this equilibrium, right, we can do some different things. So let's say we add some acid. So if we add acid, what we're really doing is we're adding H plus. We're adding H plus to this system. Well, if we add H plus to this system, what's it going to do to this equilibrium? Well, if you remember Le Chatelier, okay, if we add one of these, the system is going to shift to relieve the stress. So if we add H plus, this is going to shift the whole reaction to the left. In other words, that extra H plus will react with the NO2 minus to produce more HNO2. So that extra H plus is going to react with the NO2 minus and produce more of this. decreasing my H plus concentration again. Okay, so the pH will stay about the same. Well, what if we add a base? What if we add a base to this? Well, if we're adding a base, we're really adding OH minus. Right, so we're adding OH minus. So in this case, okay, we add this OH minus or our base. What happens with this is the OH minus is going to react with that H plus to produce pure water. Right? But what does that do to this equilibrium? Well, again, we have to look back at Le Chatelier. So we add the OH minus and it starts taking this away. And what happens when this is taken away? What happens to this equilibrium? Well, it's going to shift the reaction to the right to make more H plus. So this H plus concentration stays about the same because of Le Chatelier. Right? Once it stays the same, our pH stays about the same. So in this case, the reaction will shift right to replace the H plus ions, and the pH will remain about the same. Now, there are limits. Okay, so let's go back to our acid. So if we keep adding acid, it'll keep reacting with the NO2 and shifting left, but eventually what'll happen is we'll start to run out of NO2, and as soon as we start running out of N2, our acidity is going to get more and more and more acidic pretty quick, and our buffer solution is no longer good. Same thing with the base. Okay, so when we add a base, it reacts with the H plus, and this shifts over to the right to replace it. But eventually, what happens to this? We start to run out of it, and it can't shift right anymore. All right, so our buffer capacity, and we'll talk more about that in a minute, all right, depends on how much of the different solutions we have. All right, so this is how a buffer works. Let's try working through a problem. So let's calculate the pH of a buffer solution that contains 0.200 moles of HF and 0.100 moles of NaF in 1.00 liters of solution. The Ka is equal to 6.8 times 10 to the minus fourth. So we have HF and we have NaF. Right, so what type of buffer is this going to be? Or is this going to be a buffer for that matter? Well, what is HF? Okay, HF is a weak acid. Okay, and this is going to be the salt of that weak acid. Okay, so this is an acidic buffer. It's an acidic buffer. Right, now, we need molarities, and this is easy. So it gives us moles, all right, but we have a liter of solution. So our molarity is 0.2 molar, and this one is 0.1 molar. All right, so we know our molarity. So the molarity of this guy is 0.200 molar. All right, now, remember, this is the salt. It's going to completely ionize. So that means the concentration of Na plus is equal to 0.100 molar, and the concentration of F minus is equal to 0.100 molar. Right now, in reality, this is the one that we're worried about because this is the base. Okay, this is the conjugate base. So now, let's write that. This is the conjugate base of that weak acid. So now, when we put these together, okay, we can do something fancy and use the Henderson-Hasselbalch. Our pH is equal to the pKa plus the log of the concentration of the base times the concentration of the acid. Well, before we go any further, we need pKa. Who remembers how to get pKa? Well, pKa is just the negative log of the Ka. So pKa equals negative log of the Ka. Negative log of 6.8 times 10 to the minus 4th. So our pKa is 3.167. So now the pH of this buffer is equal to 3.167 plus the log of the base, which is this F minus, 0.100 molar, over the acid, 0.200 molar. When we do this math, the pH of this buffer is 2.87. Now, so that makes sense, okay? So we said it's going to be an acidic buffer, so our buffer's pH is 2.87. Now, I want to show you something here, because we're going to need this eventually. You see this right here, this 0.1 to 0.2 ratio? This is our ratio of base to acid. Right? And in this case, it's 0.5. Okay, 0.1 to 0.2. All right, we're going to use this ratio sometimes. Okay, we're going to use that ratio. So I just wanted to point it out here. We're not going to use it right now, but I wanted to point it out that we're going to use that ratio. Right, so now we have this buffer solution. Now what I want to do is I want to use this buffer solution. So let's calculate the pH when 0.010 moles of NaOH solid are added to this solution. Okay, so this is a strong base. So since that's a strong base, we know that the NaOH solid is going to completely ionize into Na plus and OH minus, aqueous. I'm not sure why I put that in parentheses. Let me rewrite that for you. Na plus, aqueous, and OH minus, aqueous. Now, when we add this right here is going, the OH minus is going to react with my acid. So this, the OH minus, reacts with HF, or really the hydrogen, right? So let's kind of rewrite this equation. So we know that once we put this in solution, our OH minus is going to react with our HF, and it's going to produce H2O, liquid, and F minus, aqueous. This is aqueous. This is aqueous. Well, this just turns into a nice problem. Which I'm sure you're thrilled about. we know our concentration of OH minus. Okay. It's 0.010 molar. We know our concentration of HF. Okay, it was up here at 0.20 molar. Okay. Liquid water doesn't change, it doesn't matter, so we don't need those. And we know the concentration of F minus. Okay, it's right here. All of this OH minus is going to react with this acid. So this is going to go down by 0.010. This one's going to go down by 0.010. And this is going to go up by 0.010. So we do this math. This is 0. This is 0.190. And this is 0.110 molar. Well, now that I have that, I can go right back into Henderson-Hasselbalch. All right, so this still is my base. This is my acid. So I know the concentration of base to acid again, so I can calculate the pH. pH equals pKa plus the log, the concentration of the base over the concentration of the acid. Our pKa didn't change, it's still 3.167 plus the log of 0.110 over 0.190, and we do that math, we get 2.93. That's my new pH. So after I've added that strong base, right, how does my pH change? Well, if you look here, okay, it was 2.87, so okay, it did go up, but it didn't go up very much. Okay, so just for fun, how did that change my ratio? Our ratio did go up also. Now it's about 0.58. It was 0.5. So this ratio doesn't change much, right, when we go through this buffer titration kind of thing. Right? So because the base to acid ratio does not change much, the pH changes little. Okay, pH changes little. Okay, this is a pretty typical problem. And there are a lot of steps, but I don't think it's horrible. All right. So how do we actually go about making a buffer? How do we go about making a buffer? Well, when we make a buffer, we're going to want a very specific pH. Okay, so when we make buffer solutions, we're making it for a reason. So we're going to need a solution for whatever reason that doesn't change pH easily. All right, and there's going to be a certain pH that we'll want it at. So how would we do this? Well, let's look at this theoretically first. Let's say we have weak acid HA, aqueous, which means it's going to break into and form our equilibrium of H plus aqueous and A minus aqueous. So this is our weak acid. This is our base. So Henderson-Hasselbalch says our pH is equal to pKa plus the log the concentration of the base, which would be A minus, all over the concentration of the acid. Well, when we're going to make a buffer, we want to make buffer. Well, if we make a buffer, we want the base, the concentration of the base and the concentration of the acid, okay, to have a ratio of 1. Right, so when making a buffer, we want the concentration of A minus all over the concentration of H plus to equal 1. So if that's true, what happens to this equation? Well, the pH equals the pKa plus the log, okay, of 1. Well, that just simplifies. Our pH will equal pKa. Star that. So if the acid-base ratio is 1, our pH to pKa, okay, we can figure out what system to use. Now, what this is saying is, so when we make the buffer solution, we pick a weak acid with a pKa as close to the desired pH as possible. So let's say that we want a buffer with a pH of 7.0. Which of these would you use? Would you use HF, HClO, or HCN? Okay, so they're all weak. Right? Well, I got to give you some information, or we could look it up. The Ka of HF is 7.2 times 10 to the minus 4th. HClO is 3.5 times 10 to the minus 8th. And HCN is 6.2 times 10 to the minus 10th. All right, so which one would you use? Well, before you can decide, we have to convert Kas to pKas. So we calculate our pKas. This ends up being 3.14. This one is 7.46. And this is 9.21. So if I want a pH of 7, which of these three would be the best? This one would be the best for our buffer. All right, well, how would we make this buffer? Okay, if we want this pH, or a buffer of pH of 7, how would I make this buffer? Let's go ahead and do that. How would I make it? Okay, so we're going to use HClO because the pKa is 7.46, and we want a pH of 7. Okay, well, let's go right back to the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. So we know some of these numbers. Let's put them in. So we know the pH we want is 7.00. Our pKa is 7.46 plus the log of the concentration of the base over the concentration of the acid. Well, if we do some manipulations here, we get negative 0.46 equals the log of the concentration of the base over the concentration of my acid. Right, mathematically, okay, the concentration of the base over the concentration of the acid would equal 10 to the minus 0.46. When we do this math, okay, the concentration of base to acid is 0.35. This is our ratio of base to acid. Okay, that's our ratio that we want, 0.35 to make this. So now, how do we actually do it? Well, we need to select the acid and salt. We already selected the acid. We said, hey, we're going to use HClO. Okay, and that will go into H plus and ClO minus. Okay, so I need a salt of the acid, right? So I need a salt with this negative ion in it. Choose a simple one. Okay, what am I going to put that to make a salt, a simple salt? How about Na? NaClO. Okay, so this is my conjugate base. So you just take your conjugate base and you're going to make a salt out of it. So we pick some NaClO. All right, this is our simplest salt. So we want a ratio of ClO minus to HClO. And we know that ratio has to equal 0.35. Well, instead of writing it 0.35, can I write it this way? 0.35 over 1. That's the same thing. Well, now that I know that, the concentration of our NaClO has to equal 0.35 molar. And the concentration of our acid has to equal 1.0 molar. So now, to make this buffer, all I have to do is get some 0.35 molar NaClO and some 1.0 molar HClO solutions and put them together. So by mixing 0.35 molar NaClO and 1.0 molar HClO solutions, we will make a buffer for a pH of about 7. Okay, that's how we would make that buffer. All right, last little thing, and that's talking about buffer capacity. And the buffer capacity is the amount of acid or base the buffer can neutralize before pH begins to change to an appreciable degree. Right? So how much acid or base can we add to our buffer before the pH changes a whole bunch? That's what I'm really saying here. Now, the buffer capacity depends on the amount of, that's dying, acid and base used to make the buffer. The more acid and base used, the greater the capacity. The greater the capacity. The more acid and base it could absorb before the buffer is ruined. All right, so let's just look at this real quick. Let's say we have two buffers. Okay. And they're made of the same acid and base. So let's say we have 1 molar CH3COOH, that's our weak acid, and mixed with 1 molar CH3COONA, and there's my salt. And compare that to 0.1 molar CH3COOH and 0.1 molar CH3COONA. They're exactly the same buffer. Okay, they're going to have the same pH. Right? They're made of the same stuff, same acid to base ratio. All right, so they're the exact same buffer. But which one is going to have a bigger buffer capacity? Well, this one's going to last a lot longer. Why? Because it's got a lot more of this stuff. Okay, so this one's going to have a greater buffer capacity. Okay. So they're the same buffer, same pH. Okay, same buffer, same pH. All right. This one will just last longer. It can absorb more acid or more base before that pH starts changing a lot. Okay. That's where we're going to stop for today. I think next class we're actually going to do a lab. I got to get it together. I hope I can do it. But I think the next class we're going to do a lab using buffers and letting you see some things. Make sure you're working through problem sets and textbook questions and those kind of things. And I will see you tomorrow.